Arc welding explained. Basic principles.
Thousands of years ago, soon after people had learned how to make iron, they figured out how to join two pieces of it together.
Blacksmiths were the original welders. They would heat pieces of iron until they glowed red hot. Then they would literally bang them into one piece with a hammer. This pounding process, called forging, was adequate for horseshoes and plowshares. But when it came to steel girders and gas pipes, an alternative was needed. Electric arc welding became that alternative. The process was first developed in the late 19th century when it was discovered that the brilliant white-hot surge of electricity, known as an electric arc, could melt metal and be used to join pieces together.
No longer did the entire piece of metal have to be heated. Instead, just the surfaces to be joined were melted. This is a simple concept that can be demonstrated by using a candle that has been cut in half.
The surfaces of two ends are melted. As they are melted, they are brought into contact with one another. When cooled, they form one whole. Simply put, welding is the process where two pieces of metal are made into one. All arc welding processes depend on principles of heating and cooling.
With metal used in everything from the cars you drive, to the buildings you work in, to the equipment we use, knowledge of arc welding is important.
Welding is a trade that is in high demand. It offers many challenges, rewards, and opportunities.
In this program, you'll be introduced to the basic principles of arc welding. Electrical terms will be defined. You'll be introduced to the types of components required to form a welding circuit. Let's get started.
Electricity will move at the speed of light in a circuit that is complete or closed. That's why whether you turn on a flashlight or light up a stadium, lights seem to come on or go off at the flip of a switch. When you close a switch, you are actually completing an electrical circuit. Electricity flows from a power source, in this case a battery, through wire conductors to the bulb, where the work is performed. In this circuit, electrical energy is converted into light energy.
Welding is similar to turning on a light, because a circuit is completed, allowing electricity to flow. However, in this process, the electrical energy is converted into heat energy, which is so hot that it can instantly turn metal into a molten puddle.
Because arc welding depends on electricity, it's important for you to understand some electrical fundamentals: current, voltage, and resistance.
Energy from electricity is created by the movement of electrons. This movement is called current. Current is measured in amperes, commonly called amps. Voltage can be thought of as the electrical pressure or the force that pushes the current along, much like the pressure that pushes water through pipes. In a welding shop, the typical line voltages are 208, 230, and 460. Resistance is opposition to current flow. Almost anything that current passes through has some amount of resistance, but it's at the point of most resistance in a circuit where the work is accomplished. For example, the filament in the glass bulb is the point of resistance where the work is done. In a welding circuit, the largest amount of resistance is provided by the air gap that the current is forced to travel through. Air is not a good conductor of electricity. It puts up a lot of resistance, which creates a great deal of heat. This heat is what makes welding possible.
There are several different arc welding processes. Some of the most widely used are shielded metal arc, gas tungsten arc, gas metal arc, and flux cord arc. Although they have their differences, all arc welding is done by means of a welding circuit. Let's look at the standard types of components that make up a welding circuit. A welding machine is required. Although there are a wide variety of types, a welding machine basically contains the source of power and the controls for the arc welding process. This particular model is a combination power source that can provide either AC or DC. This power source, on the other hand, can only produce DC. All welding machines, no matter which model, produce two types of voltage that you should be aware of. They are open circuit voltage and arc voltage. Open circuit voltage is the voltage established by the design of the power supply. It's the amount of voltage generated when the power switch is turned on. At this point, the welding circuit is open. Open circuit voltage is normally established between 50 and 100 volts on most welding machines. Arc voltage, sometimes called closed circuit or working voltage, is the voltage present in the welding circuit under load. This is when an arc is being struck and welding is being done. For most applications, it ranges between 15 and 40 volts and varies with the length of the arc.
In addition to the two types of voltage, all welding machines also have two important ratings that you should be familiar with: current rating and duty cycle. These ratings establish limits for the operation of the machine. The current rating indicates the machine's maximum current output. A current rating of 225 amps means the machine can deliver a maximum of 225 amps of welding current. The duty cycle is the amount of time you can continuously weld at the maximum current output without overheating or burning up the power source. Duty cycles are usually expressed in percentages of a 10-minute period. For example, this portable welding machine is rated at 225 amps with a 20% duty cycle. This means that it can deliver its peak amperage of 225 amps for a total of 2 minutes out of every 10. At the end of 2 minutes at full amperage, the machine will automatically cut off so that it can idle and cool for the remaining 8 minutes. Heavy-duty welding machines such as this one can deliver peak amperage for 100% of the 10-minute span. Welding machines are designed to accommodate a wide variety of applications. Some are portable, while others are stationary.
Let's continue to build a basic welding circuit. In addition to a welding machine, you will find two cables that are used to connect it to the rest of the welding circuit. One cable leads away from the welding machine to the work, and the other from the work back to the welding machine. Welding cables are designed to be flexible so that they can be easily manipulated and won't tire the welder when working. Selecting the correct diameter welding cable is important. Cables that are too small in diameter for the current they must carry will overheat and cause unnecessary loss of power. Cable length is also important because it directly influences the voltage drop. Voltage drop is the voltage used up, forcing the welding current through the cable. It will be greater in a long cable than in a short cable. If too much voltage is used just trying to get current through the cable, then less voltage will be available to force electrons across the air gap. Less voltage can lead to inferior quality welds. Cables perform different functions depending on the arc welding process. Some cables solely carry electricity. Others perform multiple functions, carrying filler metal, cooling agents, and shielding gases.
In any case, cables are an important part of any welding circuit. The cable leading away from the welding machine to the work is connected to the next standard component of any welding circuit, the electrode holder. In some arc welding processes, this component looks like a clamp, while in others, it resembles a gun. Regardless of its appearance, this component accomplishes two fundamental tasks. First, the electrode holder provides a path for electrons by means of some type of contactor tip or surface. Second, it provides a means for the electrode to be manipulated by the welder. The electrode is the next component in the welding circuit. In all arc welding processes, an arc is struck between a charged electrode and the workpiece. There is a great variety among the electrodes of the various processes. In fact, it's the electrode that characterizes each of the arc welding processes. For example, the electrode for shielded metal arc is in the shape of a rod or stick, giving the process its other name, stick welding. Flux cord arc is so named because its electrode is actually a very flux granules. In most of the arc welding processes, the electrode provides filler metal as well as current. However, in gas tungsten arc, the electrode does not melt, but simply provides current.
Let's look at the basic welding circuit again. The workpiece is the next component that will be found in every welding circuit. Without metal to be welded, there can be no completed welding circuit. 4 primary aspects of the workpiece affect the choices that you make as a welder. They are the workpiece's base metal, physical characteristics, position, and final use. The base metal is the type that makes up the largest percentage of the workpiece. The base metal is a factor in determining which of the arc welding processes can be used. It will also determine what sort of filler metal can be used in the welding process. The filler metal must match the base metal as closely as possible.
The physical characteristics of the workpiece will also affect your choices as a welder. For example, if you have to weld some thin metal, GTAW is often recommended because of its low heat capabilities. Other processes are better suited for thick metals.
The position of the workpiece is another key aspect that will affect your choices when welding. Welding in a flat position is the easiest to control. It's a good idea to move the workpiece into a flat position whenever possible. Anything other than flat is called out-of-position welding. This includes horizontal, vertical, and overhead. It's important for you to know what adjustments have to be made for out-of-position welding. For example, for shielded metal arc, only certain electrodes can be used for out-of-position welding.
Finally, the use of the workpiece will affect what you choose. For example, the metal track of a garage door is subjected to different stresses than the wing of a jet or a pipe used to transport oil. These 4 important factors make it clear that the workpiece is a critical component in any welding circuit.
The cable leading back to the welding machine is connected to the work with a ground clamp. This is the final standard component of any welding circuit. These metal clamps come in a variety of shapes, but all of them serve the same purpose. They provide a path for the current to flow away from the workpiece. The clamp may be attached to the work itself or to the metal table that the work is on.
You have now been introduced to a typical welding circuit. But remember, the circuit remains open until an arc is struck. Let's take a close look at how this happens.
Unlike the light bulb circuit that you saw earlier, which was closed when the switch was turned on, a welding circuit is not closed when the machine is turned on. The circuit remains open until the charged electrode is brought close enough to the workpiece to ignite a bright, flashing spark. At this point, the circuit becomes closed and current is flowing. But the electrode is not left resting on the work. If it were, a short would occur from too little resistance. Remember, it's the resistance from the current being forced to travel across the air gap that creates the heat that enables the arc to do its job. Instead, the electrode is lifted slightly away from the workpiece. The spark becomes an arc from the tip of the electrode to the workpiece. By forcing the electrons to jump the air gap, the air's resistance creates heat as high as 5,500 degrees Celsius, which is equivalent to 10,000 degrees Fahrenheit. Because the air's resistance creates the heat, the height the electrode is lifted from the workpiece determines the effectiveness of the arc. This distance is called the arc length. It can be shortened or lengthened slightly without losing the arc. However, if it is lifted too far, the circuit will be broken and become an open circuit once again.
With practice and experience, you will learn to find the proper arc length. The sound of the arc is the quickest way to tell if it's correct.
Arcs that are too short make a popping sound and may flash on and off, indicating that the electrode is striking the base metal and short-circuiting. This type of arc will offer less resistance, more current, less arc voltage, and will be a hotter arc. The arc length is too long when you hear an intermittent humming sound. This means there will be more voltage, forcing less current to flow across the wider air gap, which will present more resistance. This results in a cooler arc. Let's look at some final welds to see the effects of the arc length. Here is the weld resulting from the proper arc length. At this point, the electrode was held too far away. Notice that it has become porous. Slag has become included in the weld. During this segment of the weld, the electrode was held too close. Notice that the bead is wider. Metal has been wasted, and the process took more time. When a proper arc length is maintained, a continuous, high-pitched crackling noise, similar to the sound of bacon frying, is heard. This indicates a near-perfect relationship among current, voltage, and resistance. A steady arm and good concentration are needed to achieve and maintain this relationship.
When getting started, deliberately increase and decrease the arc length, listening for the proper sound. Experienced welders learn to use slight arc length variations as a means of controlling heat input into the work. Another thing that determines the heat input to the work is your choice of current.
DC current is called direct current because the flow maintains one direction, always from the negative pole to the positive pole. It's important for you to know, however, that the heat is not equal at the two poles. 75% of the heat is generated by the arc at the positive pole. By changing the direction of the DC flow, you can change the relationship of the heat in the weld. This is done either by flipping a switch or by switching cables. Let's say the electrode is negatively charged and the workpiece is positively charged. This setup produces a type of current called direct current straight polarity, abbreviated DCSP, or simply DC with a negative sign. Because the majority of heat is produced at the positive pole, this type of current will concentrate the heat in the workpiece. This has a usefulness for certain welding procedures. The DCSP arc is characterized by a faster melting electrode as it comes into contact with the much hotter workpiece. The weld puddle is broad, and the penetration into the workpiece is shallow. DCSP is often used where fast welding speeds and high deposition rates are required. The deposition rate indicates the speed with which filler metal is put down. A high deposition rate puts down a lot of metal quickly.
There's another type of current DCRP, which stands for direct current reverse polarity. You might also see it designated DC with a plus sign. Here, the electrode is positive and the workpiece negative. A DCRP arc is thought of as hotter because most of the heat is concentrated in the positively charged electrode. This results in a more forceful, digging arc, suitable for out-of-position work. One disadvantage of using either type of DC welding current is the problem of arc blow. DC current tends to create a magnetic field in and around a weld joint. This causes instability by deflecting the arc from its intended path. Arc blow can be dangerous, causing molten metal to splash out of the weld puddle.
A third type of current can be used to guard against this problem, alternating current. Here, the negative and positive poles are switching 60 times per second, resulting in a very hot, agitated arc. Using AC current with its rapidly changing polarity breaks up the magnetic field. The choice of the type of current that you use depends on the requirements of the finished weld, the composition and thickness of the workpiece, the welding position, and the type of electrode used. The welding instructions will often specify what type of current to use. Metal welds cannot be like the candle weld made earlier, which snaps apart with little effort.
It's important that the metals being used stay as pure as possible so that the weld can be as strong as possible. The worst threat to this purity is from the surrounding air.
If gases such as oxygen, hydrogen, and nitrogen from the atmosphere combine with the molten metal, the weld will become brittle, porous, and weak. Because of this, the atmosphere around the weld must be controlled or shielded. All of the electric arc welding processes provide for shielding with some sort of vapor or fume cloud. This cloud is either created by burning chemicals, known as flux, or it's piped directly to the weld from a pressurized cylinder. The use of flux provides a byproduct which also has a shielding effect. It's called slag. This begins as a thin covering or film that forms over the cooling metal. Along with keeping contaminating gases out of the weld, slag helps to slow down the cooling of the weld, helping to maintain the mechanical properties of the metal. After cooling, the slag appears as a crusty deposit on top of the weld. This requires additional steps. First, it is chipped away with a hammer, and then further smoothed with a steel brush.
You have now been introduced to several important principles that apply to all the different types of arc welding processes. By understanding these principles, you'll be better able to grasp the special features of each process. You've chosen an important field to be a part of because so many areas of industry depend on welding processes. If you have any questions, be sure to view this program again.